Greece, despite its small size, stands as the world's third largest olive oil producer, contributing a remarkable 18% of global production annually. Olive oil is deeply ingrained in Greek culture and the Mediterranean diet. However, most people have no idea about the byproduct of the olive oil production process: Oil Mill Wastewater, or OMW. OMW is a dark brown liquid with a pungent odor, characterized by high toxic organic load, low pH, and high levels of chemical and biological oxygen demand. When olives are processed to make olive oil, a significant amount of water is used, resulting in vast quantities of OMW. Engaging with local olive oil producers, they informed us that an average of 32 tons of olives are processed every day during the olive oil production season, resulting in the production of 40 tons of OMW that need to be managed every day, posing a challenge to the daily work. So, how is this problem being dealt with today?
While visiting many olive oil mills in Thessaly, they informed us that the most common practice for dealing with OMW is to dump it into large evaporation ponds. However, this approach is unsustainable, and if the ponds aren't properly sealed, OMW can leak into the environment, causing significant harm. For example, when OMW is discharged into water bodies, it triggers phenomena of eutrophication. Meanwhile, if left untreated, OMW harms the soil by reducing its porosity, hindering fauna development and root respiration. Regarding the regulatory framework for OMW in Greece, the responsibility for it solely relies on olive oil millers. This has led many olive oil producers to resort to haphazard waste disposal practices in the environment. So, we introduce oPHAelia, a holistic method for the bioremediation of OMW, consisting of its detoxification and conversion into a high-value product known as Polyhydroxyalkanoates, or PHAs. PHAs are a family of biodegradable polyesters that highly resemble synthetic plastics, offering a promising solution to the global plastic pollution crisis. So, considering the complex nature of OMW, we designed oPHAelia as a system in which the components of OMW, toxic or not, are degraded and utilized as a source for the production of PHAs.
Our system relies on the mutually beneficial symbiosis between two bacteria, Escherichia coli and Pseudomonas putida. We will focus on highlighting the two key processes these bacteria carry out, meaning the OMW detoxification and the PHA production. Regarding the detoxification, P. putida has the capacity to catabolize a significant portion of OMW components, especially the low molecular weight phenolene compounds, which constitute the most problematic fraction. E. coli complements this process by consuming the remaining components while secreting a wide-throat fungi lacase for the degradation of the complex polyphenolics, which Pseudomonas putida cannot break down.
P. putida also undertakes PHA production, utilizing components derived from the OMW or E. coli. To enhance production, key genes were overexpressed, with special attention given to the PHAs gene, which encodes the enzyme that links beta oxidation and the PHA biosynthetic pathway.
The PHAs gene is placed under the regulation of a free fatty acid-induced system, consisting of the regulatory protein FADR and the promoter PFAT-BA, carrying recognition sites for the protein. In absence of fatty acids, FADR binds to the promoter, causing its repression. When the levels of fatty acids are elevated, they bind with FADR and thus the promoter remains active.
While unable to synthesize PHAs natively, E. coli bolsters the production by being engineered to produce and secrete free fatty acids. This secretion is tuned through a negative feedback loop controlled by the PFR-FAPR system in an attempt to alleviate the toxicity caused by the overexpression of acetyl-CoA carboxylase, which catalyzes the first and rate-limiting step of fatty acid biosynthesis. The system works by sensing the fluctuations of malonyl-CoA levels, a critical intermediate in fatty acid production. When the system senses low levels of malonyl-CoA, FAPR is free to bind to the PFR promoter, inhibiting the expression of the LAC-I. This leaves the LAC-I repressive TAF7 promoter active to express the carboxylase, which increases the levels of malonyl-CoA, inhibiting FAPR regulatory action. The PFR promoter is now free to transcribe LAC-I, and switch off the system, causing a drop in the malonyl-CoA levels.
In certain aspects of our design, we encountered challenges that didn't have clear-cut solutions, necessitating experimental exploration. Consequently, we completed 2 engineering cycles, focused on refining the PHAs FADR system and optimizing the secretion of the lacase. Our main concern with the PHAs FADR system was the limited expression rate of PHAs, which we were alerted to by Dr. Tsabika. To address this, we conducted an experiment where we incorporated a reported gene downstream of the promoter, which confirmed that the expression levels were considerably lower when compared to a promoter of medium strength. This confirmation led us to reevaluate our design with the aim of finding a more suitable promoter. After literature review, we found 2 synthetic promoters, PAR and PLR, responsive to the FADR protein regulation. We assembled and tested reporter constructs for both, using the same fluorescent protein. This engineering cycle proved successful since both constructs exhibited significantly higher fluorescence levels, surpassing even a positive control.
Secreting the lacase enzyme was also a complex task, as signal peptides function differently in organisms from different kingdoms. Therefore, we had to undergo 2 rounds of engineering to evaluate this aspect of our design. This entailed testing the enzyme's native signal peptide in E. coli, but also design, building, and testing constructs where the native signal peptide was substituted with 3 other well-characterized peptides to find the most effective one. These constructs were fused with the fluorescent protein to measure and compare their relative secretion. Once all 4 constructs were assembled, we measured the fluorescence of the supernatant and the resuspended cell pellet after 6 hours induction with arabinose. From those measurements, we concluded that NSP4 might be the most suitable for our purposes, since it resulted in higher levels of supernatant fluorescence and greater value of supernatant fluorescence per cell pellet resuspension fluorescence.
Another crucial aspect of our design is the production and secretion of the FFAs from E. coli, where the PFR promoter and the FAPAR protein play key roles. Functioning as a malonyl-CoA sensor actuator, we believe that this system could serve as a significantly helpful asset for various synthetic biology applications in the context of the iGEM competition and beyond. Since the PFR promoter did not exist yet on the registry, we took it upon ourselves to attempt a basic characterization, building and testing 2 different constructs, before adding it as a new basic part. Firstly, in order to evaluate the expression rate of PFR, we built a construct with a promoter regulating the expression of a fluorescent protein, and compared it with the construct of a medium-strength promoter expressing the same protein. After a 6-hour incubation, we saw a quite elevated fluorescence output from the PFR compared to the positive control. Additionally, a second construct was designed with 2 transcriptional units, the reporter construct described earlier, and a transcriptional unit of the FAPAR protein under the regulation of the Arabad promoter. A gradient of arabinose was added to induce the expression of the FAPAR at different levels and help us assess the degree of repression the protein imposes on the promoter. Fluorescence measurements were taken after a 6-hour incubation, and even though the fluorescence decreased over time, the elevation was not as prominent in the samples with a higher concentration of arabinose, which indicates promoter downregulation.
Through meticulous engineering cycles, we optimized key components of our design, such as the PHAs FADR system and lacase secretion, which gave valuable insights to the inner workings of our system. Additionally, we characterized a new basic part, the PFR promoter, which we believe will have promising application from the future teams. To enhance our understanding and optimize this complex system, we have developed an ODE-based computer model. This digital laboratory allows us to explore how our system functions, test various parameters, and assess the impact of potential modifications, all without the need for costly and time-consuming experiments in the physical lab. Our team has created separate models for E. coli, Pseudomonas putida, and the PHA extraction process to capture different aspects of our project. These models are essential assistants to our efforts, and we are committed to ongoing refinements aiming for more accurate predictions about our system's behavior.
So, now that we've got a glimpse of what we're working with, let's explore how we plan to implement our project in the real world. First, we have to collect the OMW from the olive oil mill owners, ensuring safe transportation. Once the OMW arrives at our proposed facility, we'll store it and proceed with pre-treatment processing such as dilution. Next, it's important to filtrate our feedstock and sterilize it in order to prevent any contamination. Then, using our specialized bioreactor, through a fed batch process, our consortium goes into action. In order to obtain our biomass, we simply need to filtrate our bioreactor content. After that, we must recover the PHAs from our biomass by using our novel lysozyme system, followed by drying our PHAs. And voila! We have a product.
Not just yet. The last steps are the processing of PHA towards being an actual bioplastic, which is the extrusion process and the pelletization to get their final form. As mentioned before, we started with the aspiration of detoxifying Oil Mill Wastewater, a long-lasting problem in the Mediterranean region. We had some initial thoughts on possible ways to valorize the detoxified OMW, but after feedback from key stakeholders, we had to plot a new course. As we delved deeper into the research that has been done in the waste treatment field, we discovered PHAs. This was the time that we connected the dots and envisioned an OMW valorization process toward the production of PHAs with a great potential to compete with common plastic. And then questions emerged, like, sure, PHA production is feasible, but is it actually scalable? Has anyone tried to commercialize them? Wouldn't it be cool if we at least tried to do that? The answer to all of these questions is yes. Luckily, at that time, there was an entrepreneurship competition taking place, which is where we first presented our idea. To our surprise, there was a significant portion of people who recognized the potential in our venture, giving us the confidence to pursue our scheme. We attended more events and joined an accelerator program that helped us use the entrepreneurial toolset more efficiently. After constant pivots, we have managed to come up with our business plan. One thing is certain. We will try our best to put our dream up into practice, where we utilize waste towards PHAs, leaving our mark in the waste management, reducing plastic pollution, and aligning with the current policy-making efforts. But hey, you may ask, what makes you different from others in this industry? Well, our approach combines the advantages of utilizing OMW as our feedstock with the power of synthetic biology. We ensure constant and low-cost sourcing while also maximizing the functionality of our system. The result is a cost-effective medium-chain length PHA product in pellet form, utilized by many customer segments, making our vision come true.
And now, let's see how the value of oPHAelia was conveyed to the public by our human practices. To begin with, is there a better way to communicate science than a bioart exhibition also available in digital form? This initiative motivated many artists to paint for iGEM. After continuous meetings where we shared the details and vision of oPHAelia, they created art pieces depicting step-by-step our design from waste to product. At the time of the exhibition, our visitors visualized OMW in contrast to olive oil, learned about SynBio, and understood the innovative properties of bioplastic. Other events organized by our team aimed to convey the three main pillars of oPHAelia. Firstly, we hosted a seminar that attended ecologists and soil scientists to explain the severe issue OMW poses to the environment. Secondly, to make the SynBio behind oPHAelia easily understood, we organized an online webinar where specialized professors discussed the ethics of GMOs. At the same time, we visited schools to explain the concept of SynBio while writing a guide with useful information on how to build an iGEM team. Thirdly, to familiarize the locals with bioplastic as a high-value product, we hosted workshops where participants actually made the material. Moreover, we filmed a debate about the pros and cons of plastic and bioplastic. All these approaches aim to inspire and engage our local community, educating them about imminent environmental issues of today. With oPHAelia, we are on a mission to change the way industrial waste is treated and create a sustainable future for all generations to come. Let us not forget all those who brought oPHAelia to life.